All right, I had a couple questions on some of this stuff. Just to clarify, a couple of things. First question is that somebody had, and this is fairly common. How do you determine the difference between sigma 1 and sigma 2? And I brought this up earlier, but I know there's an awful lot of stuff that I'm saying, so it might be hard to track it all. The truth of the matter is it doesn't matter. The terminology on this stuff gets confusing, and I don't really know of a way around it. You can call it sigma 1 and 2. You can call them the principal stresses. You can call them the maximum principal stress and the minimum principal stress. Those words have kind of an ambiguous meaning. So the things that matter to me on this is, I guess, what the principal stresses are. The principal stresses are the maximum and minimum normal stresses in the element. You might think of them as being the most positive and most negative normal stresses. All right. Now, what's important to me is that you know what those two things are in a plane, and also you know what their magnitudes are and what angle they are at. Okay? So the biggest, in this case, the biggest compressive stress in this element, and this is the example we did in class, is what this is. The biggest compressive stress is 62.5 megapascals compression, and that occurs at 14.7 degrees. And the biggest tensile stress is 100.5, and that occurs at 104.7 degrees. Now, you can call them different things, but that's really what I'll probably ask you on a test, or what's important to you as a designer. What's the biggest tensile stress, and what's the biggest compressive stress? Because that's often what you need to design for, okay? So that's really what I want you to know, is what those numbers are, how to find them, and what angles they act at, okay? So there's other terms that are used for these things. Sigma 1 and 2 are commonly used. And you might call this one sigma 1 and this one sigma 2. I might call them different things. I might call it sigma 2 and sigma 1, but it doesn't really matter as long as you know which stress acts at which angle. It's not that important to me what you call it, all right? Unfortunately, even the terms maximum and minimum get a little bit confusing because there's different definitions of that. This isn't the best problem to illustrate that with. Why don't I see if I can find one here real quick that might be better to illustrate this with. Let's see. All right, here's 212, and you might notice the answers to 212 are negative 57.6, and what else do we got there? And 46.6. So there are the answers to 212. Now, you might, if you use the terms maximum and minimum normal stresses, there's a little bit of confusion here on which is which. Okay. This is the biggest compressive stress and the biggest stress in the element, so you might say that's the maximum stress, okay? This is the most positive stress. A mathematician might say that's the maximum stress. So that stuff gets kind of ambiguous, you know, and so, and I'm trying to find a good way to word this, but the best thing I can tell you is if I give you a problem, or if anybody does really, and you're designing that, you should be able to find the biggest tensile stress and the biggest compressive stress, and you should be able to figure out where they act. That's really how I would word it and what I would want you to know. All right. And there's other terms that are used for these things, but they're not quite as relevant because they're kind of ambiguous. So what I would like you to know on this particular problem is the biggest compressive stress is negative 57.6, and it acts on a plane at 53.1 degrees from the vertical. And the biggest tensile stress is 46.6, and it acts at a plane at negative 36.9 from the vertical. Okay, that's the bottom line right there. Okay, I also had, so any questions on that, what I'm trying to get at there? Yeah.
Can you just show me how you find that angle for the max principal stress? I was kind of struggling.
Yeah, I got some questions on that too. So why don't we just look at this one, because I've got it right up. All right, now what's going on here on this one is you've identified points A and B off of the element. Okay, so that's the stress on the X plane. That's the stress on the Y plane. Okay, those are points A and B. What those are, so what we're doing, we're going to find the angles to these. Okay, so the planes are A and B. A is the plane normal to the X-axis. B is the plane normal to the Y-axis. So that's where we start. Now notice that the reference plane in biaxial stress is this one. It's the A plane. That's what we measure everything from. So I'll probably use that, okay? So I'm going to start at A, and then I'm just going to figure out how to get to one of these stresses. And I think the easiest one to get to is that one. So if I start at point A on the circle, which represents this plane, and I rotate 73.8 degrees clockwise, I will get to a normal stress of 46.6. Okay? Now that's clockwise that I'm going. What that means is if I start on the vertical plane, rotate clockwise, not 73.8, but half of that, because the circle is based on 2 theta. For reality, I have to divide that angle by 2, and that's what, 36.9? So if I go from the vertical plane and rotate clockwise half of that angle, I will be on the plane where that stress acts. We okay with that? Now, once you've got one, you don't need to do anything else off the circle once you have one. Because if you add 90 to that angle, you'll get right there. You'll be on this plane now, okay? So once you get one of the angles off the circle, you don't have to use the circle anymore. Because if you're on one principal normal stress plane, add 90 and you'll get to the other. Okay? So that was negative 36.9. If I add 90 to it, I get 53.1. That's where the other principal normal stress plane acts, or principal normal stress acts. Okay? And then if you add 45 to it, you get where the maximum shear acts in plane. So if you find one of those angles off the circle, you're good. You can just add 90 and 45 and get the other two. All right. But the normal way I do this is identify point A on the circle, and from there I rotate to one of the cardinal points on the circle, the extreme right, extreme left, top or bottom, whichever one I want to find, okay? I just find one of them usually. I go left or right, and I find either this one or that one. The quick one was to go clockwise and get to here. It's 73.8. I already found that. I divide it by 2, so I get the angle clockwise from the A plane, the vertical plane, to the plane on which that stress acts. Okay. Once I have that, I know if I add 90 to it, I'll get the stress on that other plane. Right there, just by adding 90, I'll get to those planes, and they have 57.6 compression. So they're like that. Okay. And then if I add 45 to it, I'll know I'll be on the maximum shear planes. That's where the maximum shears are. Okay. So that would be what, 8.1 is it? So there's the planes with the maximum shears. So we okay with that? Any questions on that?
So is the compressive, the maximum compressive, that's always counterclockwise from your A position? Because I noticed on 111, it was, you moved
211, 211?
111, you moved clockwise, and then also 211, you moved, sorry, not clockwise, counterclockwise.
When you say 111, though, I'm sorry, which, that's not a problem, it'd be 211. Okay, great, okay. So, let's see. You can go any direction you want. You just have to match the direction you go on the circle to the direction you draw up your sketch and calculate your angle. Yeah. Counterclockwise positive, clockwise negative. Right. So let's look at 211 and see what happened. The problem with generalizing this stuff is the geometry on these circles is always a little different. So I can't, it's usually not you always do it this way or that way. It's you kind of make it work. So on 211, A is here. And the nearest normal stress is right there that I can see. So I am going to go counterclockwise on this one because I've already got the angle. Yeah. And that's a positive angle.
But then on 212,
yeah,
it was closer to the other side, but we still went counterclockwise.
Okay, right.
And divided that.
Right. I just did that just because I was kind of talking off the cuff here. I could just as well have gone this way. See, it always works. As long as you're doing proper geometry, it's always good.
Right.
Okay? So yeah, I could have done it this way. Just to finish the thought, so now I have to do a little bit more calculation on the angle. That would be 106.2, is that right? I think. So I'm going to go counterclockwise, 102 from the A plane. And that's going to get me on the plane where the negative 57.6 acts. So I'm kind of running out of room here, but if I go counterclockwise from the A plane, half of that, so that's what, 54.1? I think I'm doing all right here. 53.1, yeah, 53.1, thank you. There we go, 53.1 degrees. Now I'm on the plane where this stress acts, and that's compression at 57.6. And see, that's the exact same plane as that one. Okay.
Yeah.
Okay. So there's no set rule. You can go just whatever you do on the circle, go the same direction and half the angle for a sketch, and in reality to get the true angle. The circle is a model that's used to calculate these equations, and that's the reason shear is down, so that counterclockwise on the circle is counterclockwise in reality, and clockwise in the circle is clockwise in reality. They had to put shear down positive to do that, to accomplish that. Okay. We got any other questions on it? And yeah, there are keys on page 13. You know, they're right there. Okay. Okay. Questions? We good with that? Okay. Now this stuff on Monday, I won't have Morse circle on it. We'll have a Morse circle quiz probably Friday of next week is kind of what I'm thinking, unless there's something bad going on Fridays, or 2 physics tests and a differential equations test or anything like that on Friday. Okay, we're not doing that. Okay, good. So we'll just probably do it Friday, I think. Okay. So I'll give you a quiz on Morse circle on Friday. So that won't be on Monday's midterm. It'll be on the quiz on Friday. That'll take up, not tomorrow, Friday, a week from, next week, which I think is the 3rd. Yeah, so we'll plan on that, okay? And for online people, I'll figure something out on that sometime next week for you all, okay? That'll take up half the class. So you come in, I'll get you the quiz, and then we'll finish up, and then we'll cover a little bit of new stuff afterwards. Will be the plan. Okay. All right. All right, so that won't be on the stuff on Monday. So we'll finish up that review tomorrow, unless you got any other questions, or you got some on this, especially more circle. I'll take them. I mean, I know this stuff's it's tricky. I mean, you gotta work through a couple of these and figure them out. It's okay. Okay. All right. Why don't we look at that strain stuff then, if there are any other questions. So let's have a look. All right, so this is biaxial strain is what we've been looking at here just a little bit. So let's, and we kind of had to run through that pretty quick, and it's kind of frankly, a pretty complicated little derivation geometrically, and you got all the trig identities and all that. And the thing is, I don't want to spend 2 hours on the derivation. It's not really worth it. This is something where we do the strain. It's just like biaxial stress. It's the exact same idea. It's just done with strain. So what's up with this is if you know the strain in the x and y directions, epsilon x, epsilon y, and gamma xy, you can find the strain at any angle you're interested in. That's the bottom line on this, okay? And so they develop equations to do that with, which if you look at them look quite a bit like the biaxial stress equations. They have some important differences, but there's some real similarities. So the derivations here are on pages 470 and 80, and then kind of the bottom line there is on 490. That's kind of what we'll look at. And then we'll do an example here. All right, so the derivations, just to kind of touch on it real quickly, on 470, we're looking at the normal stress equation. We end up right here at this equation on the lower right of the page. And that's equation 71. And what you do is if you know the strains in the x and y directions, so epsilon x, epsilon y, gamma xy, and you know some angle you're interested in, you can go ahead and plug all that in on the right, and what will come out will be the normal strain at that angle on the left. And to derive this thing, they do it in 3 parts, and I show those 3 parts on the left. They say we've got this element that's dx by dy, and we've got a line across it at that particular angle we're interested in. So we proportion out that rectangle, so the diagonal of it is at that angle, okay, that we're interested in. Notice the angle's measured with the horizontal. That's different than stress. It's a different convention here that's used for strain. And in this case, we look and say, okay, we're going to stretch the thing out in the x direction. Let's see what effect that would have on the length of this diagonal line, because that will affect the strain at that angle. And we do the same thing for stretching it out in the y direction, and we do the same thing for giving it a shear strain. We take each of those 3 separate terms, we add them up, we divide through by the original length of the diameter to turn it into strain, and we throw some trig identities at it. And that's how we come up with this. So this equation, if we know the strains in the x and the y directions and the angle we're interested in, the angle now measured from the horizontal, we can find the strain at an angle. On the next page, we do the same thing, except we do it for kind of a shearing action, and it gets a little bit more complicated because there's 2 kind of things that we look at. The most basic thing we look at is if we apply, again, in 3 separate cases, epsilon x, epsilon y, and gamma xy, we look at how this original diagonal line will rotate. So I've got it there in a solid line. I show its rotated position with a dashed line. And we do some similar triangle kind of, we're not quite similar triangle, but a little bit of trig on some triangles here. And we figure out how that dashed line will rotate. We add up the 3 separate terms right here, and we refer to that rotation of that angled line as alpha. Again, we come up with that equation right here. So this is the alpha equation. That tells us how that line would rotate if we apply those 3 strains. That's equation 77. Now the shear strain equation, the shear strain is not the rotation of a line, it's a change of a right angle at a given orientation. So if I take that line that I've got here that I start with, and then I draw a right angle to that, that would be the angle we'd look at. So the change in this original right angle is made up of alpha plus a similar angle up here that we call beta. It's the rotation of two lines. So we develop an expression for beta, we add it to the alpha expression, we throw in some trig identities, and we get a shear strain equation at the angle, shown there on the bottom right. Got a little rest for space there, but I got it in there, okay? So those are the three equations that we develop here. And I don't think they're quite as important as the stress equations, because what stress does, that's what's going to break whatever you're building. Deformations usually aren't quite as important, but they still are something that we're interested in, so we account for these. And I'm a civil engineer, so this might be a very important thing when you're doing mechanical stuff, because if you have moving mechanisms and they start deforming and changing shape, you can get into some trouble. They'll start interfering, they'll start knocking into each other as they move, and that's not good, okay? So this is something that you would investigate to look at that. And I wrote down, what the heck did I do? Okay, this is equation 71 on it. No, that is 77. Oh, there we go. Okay. So we're dealing with equations 71, 72, and 77. Okay. All right, so on 490, I've kind of got the bottom line here. This is what we need to know. We have two equations, 71 and 72, that tell us the normal and shear strain for given x and y strains in an angle. Now, theta, the angle we're plugging in here, that's measured from the horizontal now, okay? With stress, it's measured from the vertical. With strain, though, it's measured from the horizontal. There's actually a reason for that. We'll get to it later, but there's a reason for that, okay? Now notice those look an awful lot like the biaxial stress equations. With the exception of a couple factors of 2, they're identical. So those are an awful lot like equations 25 and 26. Okay. Now the shear strain, as we've talked about, is measured in radians. Okay. It's because for these small angles in radians, the delta over L that makes up a strain is essentially equivalent to the angle in radians, okay? The shear strain is the sum of alpha and beta, those two rotations of the lines on either side of that right angle, okay? We could also get into principal strains, but I don't want to burn the time on it, but just as you find principal stresses, maximum in-plane stresses, you can find maximum in-plane strains. And they follow very similar rules. The two principal normal strains are 90 degrees apart. The maximum shear strain is 45 degrees off the principal strains, and there's equations for doing that if you're interested in it, okay? All right, we have the same sort of shear conventions there on page 500. Shear strain sign conventions. Positive shear strain makes an angle at the origin of the coordinate system decrease. Negative shear strain makes the angle increase. So that's the convention we want to remember. So let's take a look at this. Let's just look at a couple examples. Let's see what we got time for here. So let's skip ahead just a bit to 530. And let's run through an example here. So let's say that we've got a square plate as shown, and for some reason we've got a little square element that we drew in there that makes a 30-degree angle with the horizontal, okay? And then we strain this plate. We start to stretch it and compress it and put shear strain on it in the x and y directions. And so we go ahead and apply these strains to it in the x and y directions. Let's get an idea what this element will look like after we do that. So that starts off as a nice square element at 30 degrees, but then we start stretching and pushing on the plate as shown. Let's figure out what happens to that element. All right. So let's let's run that equation 71. We're going to run equation 71 and 72. So let's see how we could do that. All right, now what we got to do is fill this in right there. And just like before, we got to fill it in by looking at our sketch. I'm on page 530, I think it is. All right. Now, you got to look at the dimensions. What epsilon x is a strain in the x direction, and there it is. It's 300. That micro means 10 to the minus 6. So that's 300 times 10 to the minus 6. We're shortening up this way. We're getting shorter by 512 times 10 to the minus 6. We need to put the negative in there ourselves, okay? That side is getting shorter, so it's a negative. And here we've got 210, and what that's doing is making this original right angle here less. That's positive 210, and that's also times 10 to the minus 6.
Why is it positive?
It's positive because that original 90-degree angle is getting smaller, and that by convention is positive. And that actually comes from the stress convention. If you apply a positive shear stress, because that's shear strain, you'll get this on that on that vertical plane. The other two stresses will meet in the corners. That'll essentially will take these corners and stretch them out, and take the other corners and push them in. So you're going to end up with a shape like that, where that lower left-hand angle is smaller. I mean, that's where it comes from. So the strain convention matches the stress convention. Okay. All right. Now the angle is measured with the horizontal. Counterclockwise is still positive, so that'll be 30, just as shown. And then the other one, so that's for epsilon x1. For epsilon y1, we'll add 90 to it, and we'll get 120. So there are the angles right there. All right, so that's really the main part of doing this, is getting those numbers filled in. So we okay with that? And you got to do that by looking at the situation, okay? All right. All right, so once we've got those, we just plug them in. And, you know, it's just a matter of plugging into equations is all it is. So we got that basic equation. We got epsilon x, epsilon y, gamma xy. And we've got to find, and we got theta too. We'll do it once for 30 degrees, another time for 120 degrees. And we just plug on into that and just walk on through it. I mean, it's about all there is to it. Okay. So I just plug everything in. And I don't put the 10 to the minus 6 in there, the micro sign. I just add it at the end. That equation is messy enough. I don't need to be putting in times 10 to the 6 on every term. And I don't need to be putting in that micro metric symbol that means 10 to the minus 6 in there. I just put it in at the end. So I just run through those calculations and figure up the two normal strains. Okay, and they're going to come out to be 188 positive for epsilon x1 and negative 400 for epsilon y1. And I'm just finding those by plugging epsilon x, epsilon y, gamma xy, and the two different theta angles in there. Once I do it for 30, the other time I do it for 120. Now, just like with the biaxial stress stuff, there's a shortcut formula you can use. It's right there. So epsilon x plus epsilon y is epsilon x1 plus epsilon y1. We've got epsilon x, we've got epsilon y, we've got epsilon x1. We plug them all in. We can solve for epsilon y1. It's just a shorter version, kind of a quick formula there to plug into. Okay, so there you go. Now there's also a formula to find the shear strain too. That's formula 72. You just plug into that. So we got this, we doing all right? All right, so we got that shortcut formula, and then you can just plug into the shear formula too, and run through it, and it'll tell you the shear strain for that 30-degree angle. So the angle I'd use for that would be 30 degrees. So something like that. Okay. So this gets us the three strains. And it's like the stress stuff. I don't really think the challenge is plugging the numbers into the equation. The challenge is more understanding it and getting the initial assumptions. I don't think this stuff is used as much as the stress stuff, but I do think it's used, especially, again, I'm not a mechanical engineer, but it might be something that enters into the mechanical world. Okay. All right. All right, now let's have a look at what this means. And I've got a little element there at 30 degrees. So there's that original little element that we put on the plate. Let's have a look and see what will happen to this element after those strains are applied in the X and Y directions. Okay. All right, so what's going to happen is, now when we're doing this, when you're doing these sketches, there's different ways to do them. You know, we did that one last time where we held the lower left-hand corner as our reference point. You have to decide what your references are when you do these sketches. Now this is a sketch you see in books a lot, this style, and it's what the reference is, the lower left-hand corner plus the lower line, okay? So we're going to assume that these points don't move, so we can dimension this thing in a way. All right. So this is kind of a little bit more of a schematic. What we did yesterday was an attempt to show an accurate depiction of how that shape would look after the strains were applied. This is a little bit more of a schematic, just so we can dimension it. Okay. So let's see what's going to happen here. At the 30-degree orientation, and again, for strain, that's with the horizontal, it's going to lengthen out by 188 times 10 to the minus 6. Now, I'm going to greatly exaggerate the amount of strain here just so I can draw it and dimension it. So that little dimension there would be 188 times 10 to the minus 6. Okay. Now 90 degrees off of that, it's going to get shorter by 400 times 10 to the minus 6. So that's kind of right there. The micro symbol means 10 to the minus 6. And then the shear strain at 30 degrees is negative 598. And here's where this gets especially kind of schematic, because I'm going to put all of the shear strain on one side, okay? The reason I'm doing that is so I can put a dimension on it. Okay, so I'll kind of throw in a little bit of an arc kind of angular dimension like that, and I'll call that 598 times 10 to the minus 6. I'm rotating that line on the left counterclockwise to make the angle bigger. That's how I'm indicating that's negative shear strain. So I'm not putting signs on these. I'm showing the signs by the direction of deformation. Okay. So this is a schematic that you can use to show the dimensions of the strains. So it's really not a completely realistic sketch. It's more of a schematic is what it is. Okay. So we're doing all right with that? Okay. So what we just did there is we started off with strains in the X and Y directions, and using those we're predicting what will happen on an angled element in what we call the X1 and Y1 directions. Okay, that's what the process we just did. Now why don't we got just a minute here, why don't we look at one example here. Again, let's look at a more realistic example this time. And let's see if these equations really work, okay? How accurate they are. All right, so there's our schematic right there. That's the final, that's what that thing looks like, okay? So let's have a look and see if these equations are accurate or not. You know, they make some assumptions, they do some things that aren't perfectly accurate. Let's see how accurate they really are, okay? So let's go back a page or two here to to 510. And let's say we've got a square there, a square plate. Let's say it's 15 by 15 centimeters. So I've got one little box per centimeter. So I've drawn that at a scale, okay? And let's say, is that what did I do, centimeters on this thing? Okay. Okay, let's just say it's a square here, okay? And I've drawn it 15 squares by 15 squares. And let's say we're going to apply the strain shown there. So epsilon x will be 0.0667, epsilon y will be 0.0667, and gamma xy will be 0.2. So I'm going to stretch that plate out with the strain shown. Now, I picked those strains on purpose because they can be expressed as fractions. 0.0667 is a fraction of 1 over 15, and 0.2 is a fraction of 3 over 15, okay? And I did that on purpose so I could illustrate this with a box that's shown 15 by 15, okay? So we can do this fractionally. Now, so what's happening here is gamma, you know, the original right angle will be there. After I apply that positive shear strain, that angle will get smaller, right? So what I'm doing, I'm going to take half of this fraction and apply it to both sides. This side will be 1.5 to 15, as will that. So when I add those two sides together, they'll equal the 3 over 15 fraction for the shear strain. Okay, so alpha and beta, those rotational angles, are half of gamma on each side. That's what I'm assuming. Okay, that's how I'm going to assume that that's going. All right, so let's use that equation we just developed, and if we have those three strains that are applied, let's see what this model predicts for the strain at 45 degrees. Okay, see what this model would predict. So let's plug all that stuff into that equation and see what the strain comes out to be at 45 degrees. All right, so I'm going to plug in epsilon x, epsilon y, and gamma xy. Okay, so I'll have 0.0667 plus 0.0667 divided by 2 for my first term. My second term will zero out, so those terms go to 0 on that. The third term will be 0.2 over 2 times the sine of twice 45. That's the sine of 90, so that's 0.1. So I'm going to add everything up, and I'm going to get the normal strain that this model predicts at 45 degrees. It's 0.1667. Okay. So if I put in those values at the top, what comes out for a strain at 45 degrees is 0.1667. We okay with that? Now let's see if this really works, okay? So what I'm going to do, I'm going to take that square and I'm going to strain it with those strains shown. So the epsilon x is a strain of 1 over 15. That thing's 15 boxes long. I'm going to strain it out one more box. Same thing for epsilon y. I've got alpha at 1.5 to 15. So that'll kick up like that by 1.5 boxes, as is beta, this angle over here. Kick that one over up by 1.5 boxes. So what I'm doing, I'm holding this point as my reference. I'm stretching out both sides by a fraction of 1 over 15, and I'm kicking them over by 1.5 to 15. Okay? And what I have there in the dotted lines is what that box is going to look like after I apply those strains. Okay? And when I ran those numbers, epsilon x1 came out to be 0.1667. Okay? So let's see if that's indeed the strain at 45 degrees. Okay? Because that's what the equation predicts. All right, now, when I measure that diagonal line, I put a scale on there that you can see. That's about 10.8 centimeters, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and about 0.8 more. So that's roughly 10.8 centimeters across. Now, what this model predicts is that the final length should be the original length times 1 plus the strain. Because it's expanding out by 0.1667, it's getting 16.67% longer. When I run those numbers, the final length ought to be 12.6 centimeters. That's what this thing predicts. See? And let's have a look at it. I've got the scale on there. Let's see if it is, okay? I mean, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, look, that ain't bad, is it? 12.6, okay? So what just happened here was I knew the strain in the x direction and in the y direction. I knew the strains, the shear strain. And with that equation, I was able to predict what would happen at 45 degrees. According to the equation, it's supposed to stretch out at 45 degrees by about 16.67%. And I measured the original length, and I scaled it up by 16.67%, and it came out pretty good. Okay, it works. Okay. So that's the meaning of this. Okay. All right, so there you go. That's a little bit on biaxial strain. All right, I'll give you a couple more of these to do, but we'll put these out a ways. But 234 and 231, I think. Now these will take a little bit of time, but I'll set them out a ways. So 231 and 234. When are these going to be due? They're not going to be due Wednesday. We got that quiz on Friday, so that's probably not the best day either. How about Monday, I guess? So Monday. And this is, I'm going to have to figure out what day that is. So Thursday, 21, 28, 35th. Is that May 5th? So this is a ways out. It's not this Monday because you got your test. Week from 6th? Okay, thanks. So there we go. Okay. So there we go. Questions on anything? I'm doing all right. Okay.